So here we've got a continuous signal. You don't have to freak out too much. The signal looks like this. And we want to see what happens when we're basically going to map some of the amplitudes here to discrete values on this axis. So the first thing that we need to realize is that sometimes we can have a voltage outside of the range that we're trying to capture. So we will define some range, and we will say, like, let's say this is range divided by 2, and the other side of my range is minus range divided by 2. And here we've got some range, R, that tells me what I can capture. What happens to the samples here when I'm going to quantize, when I'm going to map it to the different levels? So anything above that level will just get basically capped to whatever your maximum range is. Okay, and so that causes clipping, or sometimes called overload noise. Now the other thing that happens, okay, normally you just make sure that your system is set up in a way that things are actually within the bounds, right? So that's kind of the standard approach. So what will happen then is you will have these like little levels. And then what's going to happen is you're going to basically map anything to wherever that level happens. Okay. What I'm going to do now is I'm just going to zoom in on this little part, just what happens in this little part here. So let's just say that we are sampling the signal at like sample happens there. Okay, and this is like NT, so some sample N. Let's zoom in on that. So we have our basically our two levels. Okay, and then we've got the signal going like zwank. This is in this little block here. Okay, and then in that space we sample. Let's say we're sampling at that point. Okay. Now we're going to make a mistake, right? This is not what we're going to transmit. Okay, and I'm just calling this signal Vn. So this is Vt, and this is V at the nth point. Okay, this is the ideal thing. In a perfect world with butterflies and everyone is happy, everyone gets flowers on Valentine's Day, we would have transmitted, and saved that value. But this is not a perfect world. So what we're actually going to submit is that value, or transmit is that value there. So we're going to make a little mistake. Okay, and we will call that little mistake E for error. E at sample N. Okay, now the point of this slide is for us to get a feeling for what is the ratio of my signal to this error that I want to introduce, or not want to introduce, have to introduce. The goal of this slide is to figure out, can I characterize basically how much power is in my signal versus how much power is in this irritating little error that I'm introducing. Okay, and we need one number to quantify that, and that number we want to be large, and that number is called the signal to quantization noise ratio. Okay, so we're going to ask ourselves, when I do this quantization, I introduce an error, how big is that error relative to the original blue signal that I have here? The signal to quantization noise ratio is basically a ratio of how much power is in my original signal versus how much power is in that irritating error that I have, and you express that in the log domain, basically a dB thing, because we want to know about small differences. We want that to kind of be emphasized, and large differences to not be emphasized. That's what the log does. Okay, so that's what we're going to do here. And what I'm going to derive now is basically expression for the signal to quantization noise ratio. And what that expression is going to tell us, if you just stick with me, is it's going to tell us what is the best thing to do in terms of choosing the number of bits and what my signal, the blue thing, should look like for quantization to not mess up my life too much. So we're going to use this little model here, and we're going to say that the signal, Vn, the real true blue signal, the perfect butterfly signal, that signal is equal to a noisy version of the signal, V tilde n, plus my error. Okay, so if I take V tilde n and I add my error, then I end at Vn. Okay, and that's just emphasized here. And really what we're going to do is we're going to say, what's the power in this relative to the power in here? Okay, to do that, we need to know something about the noise. Okay, so this noise here, what does it actually look like? And so we need to make some assumptions. What do you think are reasonable assumptions for that noise? So sometimes it's positive, like here, it's a positive value. Okay, you go from v tilde, you need to add something. Somewhere else, you might sample there, and then you need to subtract the noise. Okay, so will the noise be just positive, just negative, positive and negative? Both, okay? How would you characterize the noise? Okay, he asks about Brownian noise. I honestly can't remember exactly what that is, but I can look it up on Wikipedia. Very fancy stuff. Okay, here is, okay, so the little bit of probabilistic theory, probability theory that you're going to use in this course. E, is this a random signal? Yes, it is. To characterize a random signal, what do we use? It's a continuous random signal. Okay, so we know something else. What do we normally use to characterize a continuous random variable? 3 letters. CDF, okay, and its friend? PDF. Okay, I like PDF. The CDF thing I never really got. Okay, so the PDF, what does the PDF tell me? It basically tells me, okay, formally, if I integrate over a part of the PDF, it tells me the probability of landing in that area, or something like that. Okay, but really it just tells me how big can this thing get and how small can it get, okay, and then the probability of landing in a specific area. So I'm just going to give you the, what's the most basic PDF thingy that you can use? Uniform. Okay, I'll do that. Basically what I'm going to assume is that my error lands somewhere in the range between this and this. Okay, that's what I'm going to assume. I'm going to give this range a name. I'm just going to call it delta. Okay, delta. So all of these are delta apart. Okay, and delta is actually equal to the range divided by 2 to the power of the bits. Okay, just take that in for a second. So if I have 2 bits, then 2 to the power of 2 is 4, and I divide this range into 4 regions. Okay, and so then delta is equal to the range divided by 2 to the power of the bits. Okay, so the noise, let's get back to that. What I'm going to assume is that it's uniform in this region here. So if I'm going to write out the PDF, don't freak out, everyone will be okay. Okay, so if it's a random variable, E, this is the only time I think I'll write a random variable in this course, okay? E, it's uniform, what does that mean? It's flat, it's a little flat block. Okay, so it goes 0, then it pops up, then it goes dunk, then it goes dunk, then it goes dunk. Okay, what is the value here? What is the smallest value that E can go? Negative delta over 2, spot on. And then obviously this side is delta over 2. Okay, and then a cool probability theory question. You guys realize this is a straight line, right? What's the height here? 1 is not right. 1 over delta, that's right. How did he figure out that so quickly? He did some grade 1 mathematics, and he knew the area under here needs to be 1. He knew that that's delta, and 1 divided by delta is equal to 1 divided by delta. So that's how he figured that out. Very clever. Okay, so this is E. And that is the assumption we make for E. This might actually be wrong. I'll give you an example of when it's wrong in a second. And this allows us to get the power in my quantization noise. So P of Q is the power basically in E. Can you guys remember how to get the power from a random variable? So you basically pretend that E is a voltage into a 1 ohm resistor. I honestly can't remember this. I need to look it up every year. But I'll give you the answer. Okay. So for a random variable, the power in that random variable, if that random variable has a 0 mean, which in this case it has a 0 mean, it's like equally spread around 0, then the power is given by the variance of that variable. Okay. Just not if you now remember it. So it's just the variance in E. Okay, now you need to know what variance is, and now it gets really messy. Variance is that. Okay, the standard deviation squared. That still doesn't help me. Okay, so just nod. Everyone happy with the variance thing? Variance gives you power for a 0 mean thing. Okay, everyone is satisfied with that. So all we need to do is we need to remember the definition of variance, and then basically plug the PDF into that definition, plug this PDF into that definition, and then we will know the power. Is everyone happy with that? In real life, what would you do at this point? Cry. It's not that bad. No, not cry. What would you do? Calculate it. That's very painful. I thought you guys were going to say, ask ChatGPT. What I do is, I go to Wikipedia. So I found Wikipedia. Here's a uniform distribution. A, B. A is what's that? Minus delta over 2. B is delta over 2. Then I scroll down, and I find variance. 1 over 12, B minus A squared. Nice. Then I go here, and then I just write down what Wikipedia told me. Okay. So it's B minus A. A is minus, you can go and plug it in. It's basically delta squared over 12. Okay, just from Wikipedia. If you ever need an equation like this in the exam, I will give you the equation. Okay, awesome. So that's the variance. Let me just express this in terms of bits and the range. Because remember, the aim here is to figure out what we should do with our signal in terms of the range and the number of bits to get a high signal to quantization noise ratio. Okay, so we basically just take this delta and we plug it in there. And so we get 1 over 12 r divided by 2 to the power b squared. Okay, and that just becomes, that's an expression for the quantization noise. Wonderful. To finish the pain and suffering here, I also need to know the power in my actual signal. How do I calculate the power in an actual signal? You go and look up in your electronics course the definition of power of an actual signal. It's some integral thing with the square root and so on. The problem is, of course, before you get to that point, you need to know what your signal actually looks like. And beforehand, well, we don't actually know. So like for the quantization noise, we had a little model. Now we need another model. We need to know what the signal looks like. And we need to decide on that model. Just for this slide, what I'm going to do is I'm going to assume something just because it helps us to see what actually happens. I'm just going to assume that VT is a sinusoidal signal. VT is just the signal here that is a sinusoid with some amplitude A. And for now, let's just assume that A is like within the range of my little algorithm. Okay, and then the last thing I'll do is I'll just express the amplitude here as a fraction of basically the range. So I'll just say that A is equal to like alpha times r over 2. Okay, this is just so that something pops out of this equation and we can make sense of the result. So what does this say? It just says that I'm basically asking how big of the range am I filling with my sinusoid. If alpha is 1, then I'm basically filling the whole range. If alpha is a half, then I'm filling half the range. Everyone satisfied? Happy on the inside? Wonderful. Okay, cool. Now, what's the power in a sinusoidal signal?
Amplitude squared.
Amplitude squared, you're so close. But you're exactly halfway wrong because it's amplitude divided by 2. Okay. So yes, okay, that's close. Okay, so all we do now is we just plug this in there, okay? And we get a nice expression for PV, the power in our signal. I'm judging you guys harshly, but I need to look this up every year. So don't stress about it too much. I just remember power is like a square of something. We'll get back to power when we actually look at the power of discrete signals, okay? So where am I? Okay, I'm plugging this into this equation here. I'm taking the square, and so square root of it's 2 squared, which is 4 times 2, which gives me 8. Okay, so now I've got an expression for PV. And now the last step is, and I'll leave this for you for Valentine's Day evening, is to go and take this and plug it in there. Take this and plug it in there, and then we get the very nice expression for the signal to quantization noise ratio for a sinusoidal signal is 6.02 bits plus 20 log 10 alpha plus 1.76. Okay, that's a pretty random equation, but okay, now we've got an equation here. And that gives me the signal to quantization noise ratio for a sinusoidal source with an amplitude of alpha times the range divided by 2, and noise, uniform noise basically with a zero mean. Quickly remind me, what do we want from the SQNR? Do we want it to be high or low? Someone said low, that's wrong, high, okay? Signal to quantization noise ratio, I want a lot of signal, and I want very little quantization noise, so we want a high value. Awesome. To get a high value, what do I want my signal to be like?
Powerful signal.
A powerful signal. Okay, don't be a dumbass. You're not wrong. Okay. In this equation, where does signal feature? Where's the only place where signal happens? What? Okay, let me rephrase. There are letters in that equation. Let's ignore the numbers and the log. There are letters S, Q, N, and R, and then B and alpha. Of those letters, which one tells me something about the signal? Alpha, okay? And what should I do to alpha to make S, Q, and R go up? Make alpha bigger. The log of a big number is big. Actually, you need to make it really big to make the log of the number big. But yes, you want to make alpha big. So given that this is a sinusoid, what does that tell us? What do I want to do to my sinusoid? I want to make it as big as possible. Within limits, right? I don't want to get overload noise. So what this equation tells me is make your signal as big as possible within the range, but don't overshoot. Okay, that's not actually in this equation. That's just from the picture here. Don't overshoot. So make your signal as large as possible. Okay, now the bits. What do I want to do to my bits to get a high signal to quantization noise ratio? Okay, which letter in this equation is related to the bits? B. Okay, it's nice. It's in the letter. How do I make this thing go up? I make B larger as well. Okay, so what we've just proven is something quite intuitive, which is when I do this, use as much bits as you can and use as much of the range as possible. Okay, and we've just proven that formally here. Okay, so when I set up this microphone, like there's on the sound system here, right? When I look at the input, bah, okay. Did you see I clipped over the range? So when I set up this microphone, what I'm trying to do is make it as loud as possible without me ever clipping while I'm speaking. Okay, does that make sense? And then you use as much bits as you can, but obviously there's constraints like in life. So you can't just use an arbitrary number of bits. You need to say like, oh, this thing needs to run on a satellite, which has massive amount of power consumption, so I need fewer bits. Or I need to store all this data on a machine somewhere, and I only have a limited number of bits. Okay, and then you need to decide. You basically need to make a decision based on your constraints. Does this make sense? We made some pretty crazy assumptions here, right? Let's just talk about the source. The signal that goes in. We assumed it's a sinusoid. That's almost certainly wrong, okay? A sinusoid is right because it's nice because I get this closed form solution for the power, but this equation doesn't hold in general, right? The intuition is true. The intuition, use more range, use more bits, that's true, but that assumption that it's a sinusoid is obviously sometimes wrong. So in the course notes, there's the same derivation, but where you assume that your signal has a Gaussian distribution. Okay, so you need a little bit more of your probability theory course, but then you can go through the same derivation. You get a different equation, but again, more bits, more range helps. Okay, so go through the course notes. The other assumption that we made, and this is actually a pretty reasonable assumption, is that the noise is zero mean and kind of spread uniformly over my range. Okay. That's true in general. It's probably a pretty good assumption, but there are cases where that's a really poof assumption, that you shouldn't make that assumption. So an example of this is, let's say my range, this is the range, and this is one delta interval, and let's say my signal run is really small, so it always runs here. This is an error, this is an error, this is an error, this is an error. What can you tell me about the probability density function for this error, if that's kind of the setting that we're in? Always positive, always negative, a mix of the two? In this case, it will always be positive. To get to this point, I need to add this value. And so actually my PDF in this case will not look like the one that I had before. It will actually be skewed. It will be like more on the positive side if my signal is in this kind of weird space. Okay, does that make sense? This is very weird. Normally the signals are big enough so that you don't get in this setting, but it's just important to realize that we made some assumptions, and those assumptions might be flawed.